Hey, AP Chemisters, this is Mrs. Vandeweghe bringing you 6.5 blank wall. Um, we have so far in this chapter been talking about thermochemistry. We've been talking a lot about pistons moving up and down, so volume is changing, work being done by the piston to the surroundings and the surroundings to the piston, or on balloons or things like that, where volume is changing. A lot of chemistry, though, deals with things that don't change in volume. Go back and remember station number 1, where we had the baggies of calcium chloride and ammonium nitrate. Those volumes did not change, but we can still talk about the delta E of those systems. So here 6.5 is talking about measuring E for chemical reactions at constant volume. So if you go back and remember that delta E equals Q plus W, and work is actually negative, you might want to stick a negative in there, P times delta V. What if delta V is 0? In other words, volume doesn't change. So what happens to this term right here? It goes away. So in this case now, delta E is equal to Q, just the thermal energy. It says here the change of energy of the system is entirely due to the heat of the system. Is your thermal. So the heat given off is called the heat at constant volume, is equal to the delta E of the reaction. Now, how does this work? Okay, how do we actually calculate the heat given off by a reaction? What we have done prior is like, okay, let's heat up a piece of metal and stick it into the water. That's something very different than let's have these chemicals mix and see how much heat is given off. Because how do we actually harness that heat? It's not like heating up the copper, putting the copper in the water to heat up the water. We're having the whole chemical reaction occurring in the aqueous solution like we did in the baggies. So if we want to know how much heat this reaction will give off, we put it in something called a bomb calorimeter. And I know there's another video out there where they talk about a bomb calorimeter, and I might try to pull that one up so you guys can look at it too. Bomb calorimeters are very interesting because that is what they use to find all the calories on your food label. So did you wonder how that Snicker bar had 250 calories in it? They do is that inside this area right here, they'd put a very dried up sample of Snickers, if you will, probably put it with some potassium chlorate because that is a great source of oxygen, and light it. So there's a little ignition tube, and that's what this thing right here is, your ignition. So they're going to heat it up, and this little stir to make sure that the temperature of the water is flowing throughout the system. And here's your little thermometer. So you can actually figure out how much the water changed. Okay, and that's your calorimetry, or your calorimeter, excuse me, your bomb calorimeter. And so then you can figure out how much heat did that water in the calorimeter absorbed. Well, that's equal to the amount of heat given off by burning your Snicker bar, and then you can figure out how many calories that went to burn it and stick it on your food label. So this is a very, very practical application of thermochemistry. So every time you look at a food label, you're looking at really this bomb calorimeter to figure out those calories. So very important, I've already said, the amount of heat released by the reaction is equal to heat gained by the calorimeter. And so again, Q of the calorimeter is negative Q of the reaction. So we're going to use that. So let's see what happens. We have a real example here. So when 1.010 grams of sucrose, which is sugar, okay, which is a very good thing to know how many calories that has, if you will, undergoes the combustion of a bomb calorimeter. Okay, so how many calories, in a sense, are you getting from the sugar? The temperature of this system rises from 24.92 to 28.33 degrees Celsius. Find the delta E of the combustion of sucrose in kilojoules per mole sucrose. Watch your units. This is so important when you're solving these problems, is look at the units that they are truly asking you for. So how many kilojoules per mole of sucrose? Now notice something else, the heat capacity. Not the specific heat capacity, but the heat capacity of the bomb calorimeter determined in a separate experiment is 4.9 kilojoules per gram degree, or excuse me, that's the problem, kilojoules per degree C. There are no grams in this. So if you go back and look at our first discussion about heat capacity, you'll see these same units, kilojoules per degree Celsius. So this entire system has a finite amount of water in it. So they've already, like say, it's always 100 grams or something like that. So there is no need to actually figure out the mass here because we're used to seeing Q equals MC delta T. We don't need it for here. We know what that constant is for this particular setup. Okay, having said that, how are we going to start this whole process? Okay, let me scooch this up a little bit. Hang on, what's going on here? There we go. Okay, so where do I begin? Okay, we'll start with the reaction. Delta E equals a Q reaction minus P delta V. Once again, is there any pistons moving? No, of course not. So what happens to this term? It cancels out. Okay, so now we can find delta E, the reaction, which is negative Q of the calorimeter. Now we have something to look at, don't we? So let's see here. What is the Q of the calorimeter? So here we go. So the negative Q of the reaction, I kind of reverse the signs here to start off with, equals Q of the calorimeter, which is C delta T. How did I know that's my formula? Why isn't it MC delta T? Because look over here at your units. There are no grams here. I don't know how many mass of water I have. I don't need the grams of water. It's already been kind of figured out. So look at my units here. It's just kilojoules per degree Celsius. So it's the heat capacity constant times delta T. Let's plug in our numbers next. Okay, so Q calorie, here's my constant, kilojoules per degree Celsius. And I'll subtract here. And, you know, when I get my final answer, look at my units. My degree Celsius cancels out. So all I'm left with is my, kilojoules. And that's what I get right here. So I end up with 16.7 kilojoules. And so what's my Q of my reaction is negative 16.7 kilojoules. Have I answered my question? No, I have not. Look over here. What is it that I still need to find? I just have kilojoules. What is it that they're looking for? Kilojoules per mole of sucrose. So they gave me 1.010 grams of sucrose, grams periodic table. Yes, we're going to use that and figure out how many moles I have. So I have 0.00295 moles. Now I'm getting somewhere. So I want to know what the delta E reaction is in kilojoules per mole. It's negative 16.7 kilojoules divided by how many moles of sucrose I have. And voila, when I'm done, here's my answer. Pretty exothermic, isn't it? And again, if you wanted to, you can use your 4.18 and figure out how many calories you have and go from there. Okay, so that's how you do this kind of a problem. Why don't we try number 22? Why don't you try number 22 on your own and then see how you do? Okay, guys, so this is how I set it up. It's very, very similar to the one before. I realize that this is a bomb calorimeter, so the volume won't change. So if I can find the Q of the calorimeter, I can find Q of the reaction. So here it is. Again, it's a capital C because look at the units of the calorimeter. So I put 5.73 times the difference. So the calorimeter absorbed the energy, so the calorimeter is endothermic. So when you put the negative here for the reaction, that part is exothermic. The reaction, this burning of the hexane, is giving the energy to the calorimeter. So I got 70.2 and I multiplied this out. So the Q of the reaction is negative 70.2. But look, what is this right here? It's kilojoules per mole of hexane. So I think one of the biggest takeaways here is you have to read the problem and look at your units. Have your units determine what you need to do. So I still need to find moles of hexane, so that's what I did right here. I have 1.550 grams of hexane. This I found to be the molar mass. And so this is how many moles of hexane I have. Put it under here in my denominator, so kilojoules per mole of hexane. And I divide it out. Will you make this first zero significant? Put a line over it or something. I couldn't do that using the text function. All right, so that is the bomb calorimeter. Let's kind of see what's next. Look at this one. A little bit different, isn't it? So it says the combustion of toluene has a delta E of negative 3.91 times 10 to the third kilojoules per mole. They already gave you the delta E. When 1.55 grams of toluene undergoes combustion, the temperature rises. Find the heat capacity of the bomb calorimeter. So we are working backwards. Okay, we're working backwards. So let's go ahead and let's see what's going to happen here. Okay, so if I know the delta E is this kilojoules per mole, can I find moles here? I bet if I were to multiply kilojoules per mole by how many moles of toluene, I would find the Q of the reaction. So why don't we do that? So I went ahead and I figured out, okay, here's my delta E, look at my units. And so knowing that Q of the reaction is negative Q of the calorie, so I put the negative here, and here's the negative of the Q of the reaction. I'm sorry, calorimeter, but it's kilojoules per mole of toluene. So I need to figure out how many moles of toluene I have. Well, how did I get that number? It didn't show up. Oh, I found grams per table, so I found the moles. Okay, so all I have to do now is multiply, and I figure out the heat absorbed by my calorimeter. So there I go. I got Q-cal is 65.8 kilojoules. Now, how does this help me? What am I looking for? Well, this is going to equal to the constant times the change in temperature. So go ahead and do the rest of the math and figure out what the constant is. Okay, so here's all my work. Here's the Q, the calorimeter equals C delta T. So I plugged in my delta T's and I found out when you subtract at 14.5 degrees Celsius. So I divided both sides by 14.45 and there I got 4.55 kilojoules per degree Celsius is my calorimeter constant. So that's my heat capacity of the calorimeter. So there I go. Let's try to get the beginning of 6.6 taken care of. So enthalpy, what did I just I almost like spit on my screen here. So I'm enunciating and that's where your H comes in. So the heat involved in a chemical reaction at constant pressure. So the last time we had constant volume, what about constant pressure? So here is really the derivation of what we're talking about. Heat, or the enthalpy is the sum of the internal energy and the product of pressure times volume. So if I have a state function, there's my change in, all right, and then you notice this P delta V thing again. And look what happens is P delta V, that's for negative work, isn't it? Because positive work is negative P delta V. So negative work is positive P delta V. The works cancel out and I'm left with heat quantity is enthalpy at constant pressure. And guess what? Everything we talked about Q as far as exo and endothermic, it's the same thing with delta H. Because this Q is here, it's the same as delta H. So hopefully this will go a little bit quicker. So if the heat flows into the system, it's endothermic, the sign is positive. So how does a cold pack work? Right here, will you tell me? You saw ammonium nitrate in your little baggie. How does that work? That the ammonium nitrate absorbs energy from the water. And so the water gets cold. Okay? So heat flows from the system to the surrounding is exothermic, kind of like the calcium chloride. The dissolving of calcium chloride releases energy to the water, therefore the water got hot. We said that was, again, delta H is negative. Okay, so hopefully that makes sense to you again. Why does natural gas work? Hey, we saw that with the Bunsen burner, because heat is flowing from the Bunsen burner to the surroundings, releasing energy exothermic. So go ahead and do problem number 24 and see what you get. I'm going to pause this for a second. Wow, this is the same thing as Q from before. Sweat evaporating from skin, endothermic, your skin giving the sweat its energy to evaporate. Wood burning fire, exothermic, delta H is negative, just like before. Rubbing alcohol quickly evaporating on your skin, delta H is positive, endothermic, your skin gets cold. Gasoline burning the engine, why do you burn gas in the engine? Because you want the energy from it, so the energy goes out. All right, so it's exothermic, just like before. I think this wraps up this section. I believe the next video starts on the next page. So I hope this is helpful. Make sure, again, you watch your signs and you're very, very careful in your algebra. Take care.